Hi class, we're now on chapter 8.4. We are going from mass to mass conversions. So a chemical equation contains conversion factors between moles of reactants and moles of products. We tend to start problems though in mass, in grams, and we need to get to the grams or mass of products. So we have to always convert to moles in order to get to the next stepping stone, which would be moles of the product. So in this general outline, we would start with the mass of A being one of the reactants. We would need the molar mass, and remember the molar mass is equivalent to 1 mole of whatever the mass of those atoms. So how many of those atoms times we add all the masses together of every atom that's in that compound. And moles, and if that's a little confusing, I got examples. Moles, so then we get moles of A. We do a ratio based on a balanced equation, which will then get us to moles of B, and then we can get mass of B from molar mass of B. So here's an example. We have this equation on top, and what mass of carbon dioxide is emitted by an automobile per 5.0 times 10 to the second power grams pure octane used. So what this is asking for is you're starting out with a certain amount, and this is in grams, of octane. So we have a certain amount of octane. We want to know what is the mass of carbon dioxide that is produced from this amount of octane. So this is where we're going to go from 1 of grams and end with grams of the other product, but we have to do things in between to do that because we do not convert from grams to grams ever. So in this case, here's a little stepping stone. We have our grams. That's the mass that we're starting out with, which is right here. Then we go with the molar mass of octane. Remember, this number here is from the mass of carbon times 8 and the mass of hydrogen times 18 and add them together. And that's equivalent to 1 mole. Now we have our mole of octane and we want the mole of carbon dioxide. So we would have to do a ratio, and here's the ratio that we would do. From there, and the mole of octane is on the bottom because we want to cancel the octane out. Here, then we go to moles of carbon dioxide and then our grams of carbon dioxide. So let's solve this problem. So we have the mass that's been given to us. We have our molar mass, and if you see, we cancel out the octane, but we have 1 mole of octane. So now we do the ratio, and we set the octane on the bottom to cancel out the octane here. So we cancel out. Now we're in CO2. We set up 1 mole of CO2 on the bottom because the units that we want are on top. That's what's going to cross over to the equal sign. And this is our mass, molar mass of carbon dioxide. And based on this amount, we have 1.5 times 10 to the third power grams of CO2. So this is a good problem. Yes, it's a little bit more complicated, but this is a good general problem of how we solve doing stoichiometry. Could you separate this out? Yes, of course you can. The problem is that when you start doing a lot of problems, it's easier to do them all in one shot. And you tend to avoid making mistakes this way. Because if you have an answer for breaking this up, let's say you just want the octane, then you do the ratio, then you do this part. That's 3 different answers you have. And you might round when you're not supposed to. You might not have enough sig figs when you're supposed to have more. So if you do it all in one shot, you leave that alone. Also, this is 2 sig figs. This is 2 sig figs. Now that's not a general rule here. This, if you remember the rules, but I'll explain it. This is 2 sig figs. This is 2 sig figs. 1 mole, when anything that's a 1 is considered like a 1.000. It's an infinite. We do not touch that part. We would look at this because this is measured, but this is 4 sig figs compared to 2, so we don't need to worry about that. These are numbers that are exact that go with this equation, so we wouldn't worry about them. They don't fit into counting sig figs. And here again is a measured number, but it's 4 sig figs compared to 2, so this is why this is 2 sig figs. Let's do another problem. Suppose we want to determine the mass of ammonia that can be produced from 32 grams of nitrogen in the following equation. So you should always have a balanced equation. And now we're going to need to know how to get from one to the other. So if we have grams, we're in grams here, we need to get to grams of the other. So we're going to follow it in the same steps we did the previous one. We're going to do a stepping stone. So we start with 32 grams here, and we want to know what this one is. So here we have grams of nitrogen. we use the molar mass of nitrogen. Why do we always use the molar mass? Because the grams will cancel out with the molar mass, leaving us with the moles of nitrogen. Then we have our moles of nitrogen. We do the mole to mole ratio factor, which is 1 to 2. And then we get our moles of ammonia. And then we have our molar mass, which will cancel out the moles, leave us this time with grams, and we have our grams of ammonia. So remember, there are mole to mole factors. So these are broken down so you can see. These are what we're going to use depending on how we need them. So if we start out with 32 grams here, we need to cancel out grams. So in this case, the grams, what we're going to use, the conversion factor we're going to use is this one, because this will cancel out, leaving us with moles. Then we have a ratio of nitrogen to ammonia. So here is the equality, and here's the conversion factors. So again, we start with nitrogen, so nitrogen needs to be on the bottom to cancel out, and we're going to end up with moles of ammonia. Once we get to moles of ammonia, we need mass of ammonia. So this is again the equality, and we are going to use this one because the moles we want to cancel out, so we end up with mass. So here we go, is we have 2 sig figs. We set it up, cross out the grams. We have 4 sig figs here, so 2 still is going to win based on what we're going to use in our number sig figs in the end. Remember, anything with the 1 is exact, so we don't worry about those. Then we have our ratio, again, exact. 4 sig figs doesn't beat 2, and so our answer is in 2 sig figs. And hopefully you see how we cancel out everything until we only end up with the units that we want. And when I write these problems out on a piece of paper, before I do anything else, I write this here, I leave space, I write an equal sign, and I write just the units that I need to have the problem in. Because that will tell me if I fill this in, if this doesn't match what I've written here, then I didn't set it up right. Something's wrong. Okay, so one more. I think this is one more. How many grams of oxygen are needed to produce 45.8 grams of iron 3 oxide in the following reaction? So we're not even going to worry about A, B, and C. We're just going to solve the problem. But what's it asking for? So we have a product, and we want to know how much oxygen was needed to produce this amount of product. So again, we do a stepping stone. So you can see we start with grams. If you haven't noticed, it's a recurring theme here. It's not really changing. The compound may look more difficult, but the steps, they don't change. If you're in grams, get out of grams. How do you do that? With molar mass. When you get to moles, what do you do now? You do the ratio based on the balanced equation. Once you do that, you get to the moles of hopefully your product, use the molar mass of your product, and now you're in grams. So the steps are not changing, even if the compound and the equations are. Again, here is your equalities and conversion factors on how you need to set it up, but you have the flexibility to set it up how you want to. So this is why you need to look at the units and set up the units correctly, or your answer will be wrong. So we have 45.8 grams. We take the molar mass of our iron oxide, cancel that out, we end up with 1 mole of iron oxide. We use the ratio, which is 2 to 3. That gives us 3 moles of oxygen. Cancel out the iron oxide. 1 mole of oxygen gives us, and this is our molar mass, remember, this gives us our grams. Multiply everything, divide by what is on the bottom, and we end up with 13.8 grams of oxygen. That is 3 sig figs, so this answer would be B. All right, one more. The reaction between hydrogen and oxygen produces 13.1 grams of water. How many grams of oxygen is reacted? So I'm just going to jump through because hopefully you guys are seeing the trend of what's going on here. And you see where these equalities and conversions are coming from. Do you have to write these out? Of course not. But you should be able to be comfortable using it how you need to in order to solve the problem. And then here's the problem. It's all worked out. Hopefully this makes sense. Again, this isn't any different from any of the other problems I've been showing you. 3 sig figs, the end.